some GFS experiments with CAM physics as part of real-time reservations. George?
All right. So this will be somewhat of a different talk, and I'll get to that in a little bit. And we will be focusing on the global runs with RRFS, also called CAM physics. RRFS stands for Rapid Refresh Forecast System, probably derives itself from the RAP-HER, and the CAM for Convection Allowing Model. So can you, next slide, please? Okay, the last time I was here to give a talk at HFIP was in 2018. And back then we had only replaced the convective parameterization. And back then we showed good statistical results for track and intensity compared to GFS physics. For this year's experiments, we're using a larger part of the RRFS physics. And that means we are also using the Thomson double moment microphysics scheme, which is also part of the UFS R2O physics project, the GF convective parameterization, as well as Joe Olson's MYNN EDMF turbulence scheme. So first I have a few slides on that. Then I will go on to show some commonly used global statistics, such as hydronormally correlations, comparisons to radiosondes, and comparisons to GFS analysis. I will then also explain some of the issues we found with the Thomson microphysics scheme and tell you what is next, and also what we will be using this data set for. At this point, as I mentioned, I don't really have a completed statistical analysis of tropical cyclone stats. That's because the guy who used to do this a couple of years ago, unfortunately, just retired. So this is probably a talk where you hear the least about hurricanes. If I have some time, I will present some at the end on IOTA, just to have something in there with hurricanes. Next slide. So the first would be the turbulence scheme, which is Joe Olson's MYNN EDMF approach. Is an eddy diffusivity mass flux scheme. And most people will know this scheme. It's used in many different modeling systems by now, such as WRF, MPAS, FE3, different CCPP versions of FE3. It is tuned to LES simulations, single column model testing, and also to improve key for forecast objectives in your operational RAP and HER, such as boundary layer temperature, moisture, winds, ceilings, cloud cover, and shortwave radiation downward. And there is a couple of things that are new that haven't been used before in longer tests. One is the improved conservation of scalars in momentum. And if you go to the next slide, and also the mass flux scheme now tapers off at very high surface wind speeds. So very near hurricanes, the mass flux scheme would actually not be active. All right, next slide. The GF scheme has been around for a while too. It's used not only in WRF, RAP, HER, MPAS, also in NASA's version of FE3. As a matter of fact, Saulo Freitas, the F from the GF scheme is very active in further developments. And a recent submission by Saulo, as well as myself, to GMDD describes some of the latest changes. Short mass flux, for example, is usually an important parameter in convective parameterizations. And people spend a lot of time making assumptions about what entrainment and detrainment rates should be. But we're going a different route by assuming that the statistical properties from deep convective plumes are determined by a characteristic cloud size and a PDF that determines the vertical mass flux distribution. Once we have that vertical mass flux distribution, we can derive entrainment and detrainment. Level of maximum mass flux is determined by stability profile. For deep convection with single column model results, we have shown that this works actually really well, significantly better than other convective parameterization approaches. That's for the mass flux profile. We have 3 PDFs for deep, congestus, and shallow convection. Cloud water detrainment proportional to mass detrainment and in-cloud cloud water ice mixing ratio, where the proportionality constant is a pure tuning factor. Cloud-based, below cloud-based evaporation, we can now do in shallow convection. And we had to change the subsidence terms for cloud water and ice to avoid negative mixing ratio. This came in because of a requirement also for tracer transport. And Hannah Barnes included the double moment microphysics tendencies to feed back to the Thomson scheme. That's also new for this HFIP runs. Next slide. All right, we decided to go with our most up-to-date version of the modeling system. Are you seeing this whole slide, or is this, because I can't see everything here, but.
We can see most of the slide.
Okay.
We can see the red box.
All right, sounds good then. So our official HFIP run was the one with 64 levels. So wherever it says RRFS L64, that's our official HFIP run. And we're comparing that to our own experimental run with 127 levels, as well as EMC's parallel version 16 run. EMC's run with 127 level is, of course, using GFS version 16. That's a somewhat different analysis. Our stuff runs with a version 15 operational analysis. And if we look at these results for high anomaly correlations, for the Northern Hemisphere, it's pretty much the same for at least the 64 level version compared to EMC's 127 level version. For the Southern Hemisphere, we're behind. This is somewhat different than what we found before in our real-time run. Go to the next slide. This shows the differences of the ACC scores comparing to the operational 64 level run, not the 127 level parallel run. And this was a model that was run before HFIP, though. For HFIP, we switched. This is a 9-month average. And there we actually have, again, similar for Northern Hemisphere, but improved results for the Southern Hemisphere compared to EMC. And certainly the 127 level run is not worse than the 64 level run. So we're looking into why this is the case for the HFIP runs. Okay, next slide. This is going back to the HFIP comparison. This slide shows a comparison to global radiosonde observations over the 3-month period. What is obvious here first, on the left side is a warm bias in mid and upper levels. That is worst actually for the high resolution run, vertical resolution. The 127 run, there is a warm bias all the way from 850 to 200 millibar. On the other hand, on the right side, the wind bias looks improved, especially for the 64 level run. Okay, next slide. Makes sense to also look at comparing to analysis. Now, we didn't have time to pull all the 168-hour forecasts down. So this is only looking at 10 different runs, but the results are pretty much the same everywhere. You can see that actually, if you would look at comparing to analysis, the warm bias in 127 level run would be significantly worse. It's just there's no radiosonde observations, of course, over the Pacific. Pacific and also Indian Ocean there. And even the Caribbean area. So, and this is particularly strong in 300 and 500 hectopascal areas. Next slide. Just another way to look at it is actually a zonally averaged two-dimensional plot from South Pole to North Pole. And again, it shows up pretty drastically with a fairly good-sized warm bias in 127 level run. Next one. Interesting is also to look at the wind speed error profiles relative to the GFS. Now, this is again compared to the GFS operational runs. And it looks like, if you look at the biases in the lower part, everywhere the wind speeds are higher when using the RFS physics. I don't know whether this would be comparing the same way with the current version 16, but if I remember looking at the Radisson observations a few slides ago, that seems to be still the case. Certainly, we're still higher in wind speed everywhere. And strongest differences are in the upper levels. Next slide. So one thing to look at also is total precipitation. This is kind of interesting. If you look at the zonally average on the very right side over the tropics, that's actually a very good comparison. It's almost right on compared to iMerge. If you look at the differences in the precipitation amounts, 64 versus 124 levels, you do see somewhat a little bit more precip over the areas where there was a warm bias. So zonally, it might end up to be perfect, but if you look at regional differences, there's definitely differences. If you look at the lower row there for 127 levels, there is an overprediction over the Pacific, the tropical areas, and also in the Indian Ocean area, where we did see a warm bias. And there's also very light overprediction in areas where you usually get a lot of shallow convection and congestus type convection, maybe. Next slide. So to break this up even further into convective and or resolved and non-resolved precip, interesting thing here is what you see with increased levels, you actually see more non-resolved precip and less resolved precip. That's a little bit counterintuitive to me. I'm usually used to seeing more precip with either or more large-scale resolved precip with either higher horizontal or higher vertical resolution. That's kind of interesting. So that is, as I said, somewhat counterintuitive. Something similar was found by Saulo, though, with NASA's FE3 version, and he contributed it to shallow and congestus clouds. However, cloud radiation coupling is important too. Next slide. So we were looking into this a little bit further and found something else interesting. I mentioned the first few bullets here already. Let's talk about the last two. Pacific maritime areas usually have low aerosol concentration. Does outer conversion maybe need changing in the convective parameterization? Now, the GF scheme is currently being tested with aerosol awareness to make it more consistent with the Thomson scheme, which is supposed to be aerosol aware. So we asked the question, what do Thomson aerosols actually look like? You go to the next slide. And we were very surprised. The upper plot here is the Mehra 2 analysis. Then the middle one's a 124-hour forecast using integrated water ice-friendly aerosols, which is what Thomson uses. And then the 10-day forecast, and you see that you end up with a ton of aerosols in the Pacific, in the tropical areas, which is just not correct. So what do you do about that? You go to the next slide. Well, we actually have a model that's just been implemented, GAFS aerosols, in September, that has much more realistic aerosol distributions. And we can actually use this in a very simple way. GAFS aerosol uses the big NUOPS component where all the purple boxes are combined into one component. But we also have a version at GSL that uses CCPP, where every process is a separate CCPP routine. While GAFS aerosol has 19 variables, what would be way too much computational burden, since Thomson already has additional variables, we can do it in a much simpler way. Hit the return button, hit the next slide. What we do is we take the low-cut chemistry out, and we take the 19 variables out. In that case, we have no additional computational time. We have 0 additional variables. We have a little bit addition because of all the emission routines, the purple boxes just to the left of the variable box. But the computational burden, additional burden, is very limited. Next one.
George, you have 5 minutes. Please keep that in mind.
And this is very similar to what we're doing in the wrapper smoke, except now we will include all other major aerosol sources. Next slide. The things to come. We obviously need objective track and intensity verification for the current results. We will use the HFIP data set, which will be of significant value for the UFS R2O project. The Thompson scheme is a major focus in that project. We feel like, even though we don't have statistics to prove it yet, that the tendency limiter that is in the Thompson scheme may still be a little bit of an issue. I think, or we think, we have slightly lower tropical cyclone intensity. We will rerun a period with realistic aerosol distributions. That's something we have really big hope in. This is actually, by the way, something that does not show in the RAP-HER runs because they only integrate over a day or two. And we really feel like we need to include data simulation. We wanted to do this for this run, but we couldn't. Workflows weren't going right. So this would be important because data simulation depends on the physics too. We'd like to use the same period to rerun with both the Thompson aerosol aware scheme and the GF aerosol aware scheme with the aerosol distributions, the improved aerosol distributions from above. And we also like to use 3 to look at aerosol impact studies on S2S scales in comparison to GEF's aerosols. And that's because this is actually cheaper than GEF's aerosols, but will include both radiative and microphysics impact. Okay, next. I can't leave completely without any hurricanes in here. So here's just, I had to bring up Iota, a really interesting storm, I thought. This is a beautiful picture from I guess for a lot of people, horrific event too, back in Nicaragua again, I suppose. Go to the next slide. Yeah. And we did this actually on a week-by-week basis. We compared every week, almost all the storms that happened, but we just don't have statistics from it. This is just one example from a 5-day forecast between the different runs. On the lower right, 964 is observations or the verification. And notice GFS 966, RFS 969, both actually very close, closer than all the other models. However, of course, the track is further north, so it's misleading here too. ECMWF for this particular case seems to have the best track, but also only a 992 storm. But it's over land. What do you expect? Next one. I'm almost done here. This is just my last slide, I believe. This just makes it important to know that without good objective statistical evaluation, it's impossible to say one model is better than the other. You can see on the left side, 120 hours, beautiful there from HMON, almost right on in the intensification and even in the top speeds. The blue crosses is RFS physics. The blue line is aviation. On the left side, we look significantly better than the regular GFS physics. On the right side, just one day later, it's the opposite. So, of course, all of that also depends again on track, and H1 doesn't look that good anymore either, one day later. So we really need overall statistics. And I believe that's it. Go next slide. Yeah.
Okay, thanks, George. We have maybe 1 minute for a quick question. Frank, you had a question in chat?
Yeah, George, I was wondering about your using index. You turn on the
Yeah. I didn't.
Okay, because we've been looking at that, and that seems to be an important area.
George, you're on mute.
I believe that TKE advection is turned on in NYMN, but I am not 100%. I'm like 98%. But I can find out.
Thanks.
Okay, we need to move on to our next presenter. Thank you, George. Our next presenters are Jonathan, Lynn, and David. Jonathan, are you presenting?
Yeah, I'll present the first half, and then David will present the second half.
Okay, all right. So they come to us from NCAR, RAL. Jonathan, all yours.
Thanks. Yeah, so this is a little bit of a different presentation from the things we've seen this afternoon, and this is a little bit of applications of of the products that that have come out of the HFIP project. So next slide, please. Oh, yeah, and yes, I'm from MIT, not NCAR. So I want to talk a little bit about Flow, which is a large ensemble model. It's nicknamed Forecast of Hurricanes using large ensemble output. Next, please. And it's a 1,000 member synthetic ensemble. Really, you can use as many ensemble members you want. But the key idea that we wanted to incorporate when we developed this was the large-scale internal variability that you can get from ensemble models. So the spread in the ensemble models, at least in the large-scale environment, is what we're trying to take into account in this ensemble, in this large ensemble model. And you can see more from our paper that we published earlier this year for more details. Next, please. I won't have time to go through all the details of the model, but in general, this is just a flow chart of the information. So we take information from a numerical weather prediction ensemble model, and from that we bootstrap a bunch of synthetic tracks from the ensemble model. So we just create tracks that are statistically similar to the ensemble tracks, and then we take environmental quantities from the large-scale field, like the vertical wind shear, the mid-level relative humidity, and we feed that into an intensity model. The intensity model is, there's no such thing as free lunch. So in order to run a large ensemble like this, we use a much simpler zero-dimensional intensity model. So with that, we sacrifice a little bit of the mean state accuracy in hopes that the probabilistic component will give for some kind of quantification of uncertainty. And finally, after the intensity model, we put that into a surface wind model to get wind speeds. Next, please. We have been running this in real time for about 2 years now, but they're late cycle forecasts since they're drawn off the ensemble models. We started running the European ensemble last month, and then the GFS ensemble has been running for a while now, but we moved over to the new version in September. Next, please. So this is just an example of a forecast. This is for Hurricane Delta. What you're seeing here is the red lines are the 5th, 25th, 50th, 75th, and 95th percentiles. And they're just different scenarios of what could happen. And this is using the European ensemble fields. And obviously I cherry picked this example because it ended up working well, but this is in general what you would see from the intensity fields. But I think what we want to emphasize is more of the probabilistic nature of the forecasts. So what I'm going to show from here on are the probabilistic verification metrics. So if you can go forward, please. This is an example of a pointwise wind forecast. So what we want to focus our model on is the probability of observing wind speeds at a particular point. So this is for the I think this was one of the most recent hurricane that made landfall in Nicaragua, and this is at Puerto Cabezas, which is on the east coast of Nicaragua. And the top panel is the instantaneous wind speeds observed at a point, and the essentially you have a PDF in time, and then the bottom is just that probability but accumulated over the forecast period. Next, please. In more traditional sense, I've done the verification of the reliability of the exceedance wind speed. So this is cumulative over the 5 days for all of the storms that we've run the model on in the Atlantic and Eastern Pacific. The insets here are the sample sizes for each of the probabilities. There's a bias in the 34 knot wind threshold. Sorry, the different lines are the different thresholds, the 34 knot, 50 knot, and 64 knot wind thresholds for the GFS ensemble. And it's something that we're aware about and are working to fix. And for the other thresholds, it seems okay. Next, please. This is also the same verification, but from the European ensemble, there are less. We had less samples because we started running it last month, so this is only out to 4 days, but it's pretty much the same story. Next, please. Next again. Sorry for all the animations, so this model flow was developed with probabilistic forecasts in mind, and really the key point that I want to emphasize here is that we're trying to incorporate the state-dependent uncertainty by leveraging the ensemble models. Some other future work that some people have, or some individuals have wanted uncertainty quantification, but maybe the mean state of the model we've sacrificed a bit. And so here we are trying to develop a mean state nudging term that can shift the mean forecast toward the desired forecast, like, for instance, HWRF. And some other things that we're experimenting with are 7-day or longer forecasts. Whether or not this is actually predictable on a point-wise scale is something that we're also looking into, but hopefully we'll be able to answer. And I'm happy to converse offline with anyone. There's my email, or if you have any questions or suggestions for improvement. Thanks, and I'll hand it over to David John now.
Thank you, Jonathan. So we're going to change track a little bit and talk about another set of kind of post-processing methods to look at rapid intensification. We're focusing on machine learning and deep learning for this, and the goal here is to develop machine learning-based post-processing methods for high-resolution hurricane models to improve. In particular, we're targeting intensity prediction. What we want to do is take advantage of all the kind of structural, dynamical, and physics patterns that there's some kind of systematic bias in like HWRF or HAFS or one of the other models. We can kind of identify those and use that to bias correct the model and come up with a better forecast. We're also interested in things like uncertainty quantification, basically seeing probabilistically what are the chances of rapid intensification, and basically show that this can be done with an operational model. For this, we're targeting HWRF, but the framework we're using can be applied to any other future system like HAFS, that as long as there is a sufficient set of reforecasts or other archived forecasts of a similar model configuration. Next slide. The training data we're using for this particular analysis is the H220 configuration of the HWRF. We use the reforecasts from for H220, which contain forecasts from 2016, 2018, and some of 2020 or 2019 for our training and validation. Then we're doing our evaluation itself on the real-time 2020 forecasts. So there's some statistics on what we have. As far as our processing, we take all the HWRF runs and calculate these ships-like predictors that describe the environment in or core of the tropical cyclone. Then we also pull out the 2D fields of tangential, radial wind, and equivalent potential temperature at 4 levels, so surface, 850, 500, and 200 hectopascals. We rotate all the fields by the 850 to 200 hectopascal shear vector, so similar like structural features should appear in roughly the same location. And there's all the stats here on exactly how many forecasts we have for each basin. We train on all basins, so there's not a separate model for Atlantic versus Pacific. It's all thrown to the same pot. And what we're targeting is the 24-hour time difference between the beginning and end of the intensification period. So we're going to calculate the change in intensity over a 24-hour period at each lead time where we have that the availability to do that. One key thing we do with the data, or input data to go along with this, is we also calculate the time difference over that same period. So we take like the difference of the theta E field at forecast hour 30 and forecast hour 6, and so if the hurricane is not changing structure significantly in that period, then the field should be near 0. But there are significant changes, you should see it in that time difference field. And the same with all the other SHIPS indicators. We also look at the differences. And that's our main input to the model. Next slide. For our machine learning, our kind of baseline method is a densely connected neural network, which just has a couple hidden layers and raw U activation function. Basically, sort of kind of a relatively simple baseline, but obviously more complicated than like a logistic regression, but still not as complicated as the deep learning models we're testing. All the deep learning models we're testing are in the convolutional neural network framework. We set them up to predict the discrete probability distribution of the 24-hour change in intensity. So we have 5 knot bends between -40 and 40 knots, and the model just predicts the probability in each bend. So you get a kind of a discrete PDF. You can take this discrete PDF and get an expected value out of it by multiplying the bend probability times the bend value if you want to get a kind of more deterministic forecast. We test a few different key variations here. One is the loss function. So our base loss function is something called categorical cross entropy. This is a pretty standard loss function for classification problems in machine learning. There's also a variation on it something called focal loss, where you take the original cross entropy, this log p times the probability of what was actually observed, and you add on this other regularizing term, this 1 minus p of the observed class plus this tunable parameter gamma. And what this effectively does is it helps spread out the probabilities across different bends, so that it produces a kind of a smoother probability distribution than what categorical cross entropy does by itself. We also test 2 different architectures. One is this I call the base architecture, which is a series of convolution and pooling layers. So the convolutions basically just do a kind of a small filter over a subset of the image, and it multiplies the convolutional filter weights by the values in the image across all variables, and sums them all together. So you do this multiple times, and then the pooling reduces the dimensionality of the image by just taking the mean in like a 2x2 box. And so we just basically create more features as we run more convolutions. We then flatten out our final vector, feed it into a fully connected layer, and then into our probability bins at the end, which is that 17 number at the end. We also, in addition to doing regular convolutional layers, we also do something called residual layers, which is ResNet. This kind of model has worked really well in image processing problems, so we wanted to see if it could also pick out additional features that the regular convolutional neural network could not. And the final thing we added, and this ended up being very crucial in this particular problem, was doing dropout, which basically you're randomly setting either individual neurons or whole like kind of channels, which are sort of you can think of it as like individual variables, outputs of a convolutional layer, setting them to 0. It's meant to force the model to be more independent, and it helps prevent overfitting. Given the limited number of examples we have in the hurricane data set, we were getting some. The model was kept overfitting constantly, especially any of the deep learning models were overfitting significantly. So just adding this dropout and made a huge difference there. Next slide. First we're going to show the deterministic results. The green line is the HWRF, basically deterministic intensity forecast, the mean absolute error of that at different lead times. And then the other lines are the the blue lines are convolutional base and convolutional focal, which is the light blue. And then the purple and light purple lines are the ResNet, base, and focal, and then the red line is the dense neural network. So a few takeaways, and on the left we have the Atlantic Basin MAE, and the right is the Eastern Pacific MAE. We generally see that the HWRF, the machine learning models aren't really competitive or about the same as HWRF for early lead time, so like 24 to 48 hours. But after that, HWRF seems to get worse, and all the machine learning models seem to consistently improve on HWRF in terms of MAE after about 48 hours. This has also happened in the last version of HWRF with our deep learning approaches. So this seems to be a common thing. The ResNet one seemed to do consistently worse than the base convolutional models. The focal loss doesn't seem to make a huge difference in terms of MAE, but you'll see it makes a difference later on. So next slide.
David, you have 4 minutes, 3 minutes.
Okay. We can also show we're getting skill at predicting rapid intensification. So this is the area under the rock curve for 30 knot or greater probabilities, and we see that the dense neural network does the best, but all of them have skill at doing this. Then we go to the next slide. We also look at the reliability diagrams, and we see that all the different machine learning models are generally fairly reliable. We do see some under forecast, kind of underconfidence bias in the ResNet and the dense neural network, but the regular convolutional ones are pretty right on the one-to-one line for for both base and focal loss. So that's good to see. On the right, we have a performance diagram that it's kind of another variation on the rock curve, except it works better for rare events. And we see that the dense neural network seems to have some better discrimination skill than the deep learning models, but they're all fairly, I would say, fairly competitive. Next slide. We can also show this for like an individual case. So this is from Hurricane Laura this year. The orange line is HWRF's forecast, and the red line is the best track. We see that the machine learning model, the deterministic, the machine learning models kind of don't actually get to the RI threshold, but if you look at the probability, the PDF, which is the kind of filled values in the background, there are non-zero RI probabilities here, and they go up about right around the time we get to the actual RI period for Laura. If you flip to the next one and flip back and forth a couple times, you can see using the focal loss, the probabilities kind of spread out a bit more. Or flip back one, sorry. Basically, you can see that when we go back and forth, there's less mass in the center and more spread out to the edges with the focal loss. So I think this can be advantageous for getting better PDFs at the extremes. So next slide. Finally, wanted to talk a little bit about interpretation. One thing we want to do going forward more is looking into what, especially with the convolutional neural networks, what spatial features in the storms are important for prediction. This image it should be like an animation, but it may be having issues. But it's a saliency map, which kind of shows areas where how the wind field or whatever field you have should change to, say, increase the probability of rapid intensification. So you can use this to interrogate our models better and identify areas to focus on to determine, like, kind of, if we see this happening, maybe we should increase our RI, like human probabilities. There's also another technique called layer-wise relevance propagation that's related to saliency maps, but is more for saying what areas are important for this, what the prediction we actually want to give. So I think they complement each other really well, and as part of the kind of AI Institute based at University of Oklahoma, we're going to be looking more into both of these methods for problems, including tropical cyclones. So in summary, next slide. We find that all of these things, the time difference fields, the discrete probability distribution, and dropout really are important for getting good, like a deep learning model that actually fits and has skill at predicting RI. And focal law seems to add some icing on the cake in terms of getting smoother probability distributions. So I think they're all things that can be easily incorporated into all kinds of different machine neural network frameworks, and should consider those going forward. Now, I saw there's a few questions, so I'll try to take these. First one is, how does the intensity bias look like compared to HWRF? What I've seen is that the it tends to be more reliable, but also is like reduces the range of values. So it's like the deterministic forecasts tend to be more like have a negative, bit of a negative bias, and more so than HWRF. So it's more, in general, it's more conservative. I have not converted the HWRF forecast to a probability, but I do want to do that. At least do like a simple logistic regression fit to the to HWRF, just to have a probability baseline. And then another question: can you use layer-wise relevance propagation to look at the vertical coherence of the wind field that we see in RI cases? Yeah, that's certainly something we could do. And I've done this with hailstorms and with saliency maps, and there does seem to be it does seem to be able to pick up on how much in the vertical things are overlapping. So that's something I can also look at for the hurricane data. Any other questions before we have to wrap up?
Okay, hearing none. Thank you, David. Thank you, Jonathan. And thanks to all our speakers with the session, real-time reservation experiment. They all did a great job. So we